want our attendees to know that our company has a long history of working with the construction materials industries. Our scientists and petrographers are part of ASTM, ACI, ICRI, ASCE, and RILEM. At the company level, we are accredited by AASHTO and have validation by the U.S. Army Corps of Engineers. How do we work with your industry? Well, in industrial hygiene services, we provide analytical services for OSHA compliance, including respirable crystalline silica, metals, etc. We do in GHS and regulatory compliance, we do product analysis in support of GHS, HAZCOM 2012, CalProp 65, and other regulatory requirements. For product validation and quality assessment, we provide analytical services to verify the chemical and physical properties and purity of raw metals. And in failure analysis, we work in evaluating concrete elements that have undergone distress. So let me introduce you to our speaker. This is April Snyder. Ms. Snyder has over 20 years experience in concrete petrographic studies and serves as the Construction Materials Laboratory Manager at RJ Lee Group. She conducts evaluations of concrete materials to identify failure and distress mechanisms using petrographic techniques in combination with chemical and physical testing. April is a past president of the American Concrete Institute, Pittsburgh chapter, and remains on the board of directors there. And she serves at a chair level of several technical committees at ASTM and ACI dealing with our topic today, aggregate reactions in concrete. So, April, thank you for joining us today. Give us 1 second, and the floor is all yours.
Okay, hello everybody. Hopefully you can hear me okay here. Thanks for getting on. We are going to talk about aggregate reactions in the framework of concrete durability. Concrete is the most widely used construction material in the world. When it's done right, it can provide decades of service with little to no maintenance. But the conditions of exposure and the use will affect the performance and service life. So the concrete needs to be designed, proportioned, transported, placed, finished, and cured properly in order to achieve its intended service, which some applications are expecting to be upwards of 200 years. The aggregate comprises about 70% of the hardened concrete by volume, and they're more than just fillers in concrete. The aggregate properties greatly influence concrete performance and strength. Qualities of the aggregate can affect the ability of the fresh concrete to be properly mixed and placed, which then can affect the hardened properties and the durability. Many of the negative qualities and properties will be flushed out with preparation and testing to meet the requirements for concrete following ASTM C33. And in addition to specifications that are specific to the application, which may include some additional testing and validation of quality. When we talk about concrete durability, there are several of the most common mechanisms known. Corrosion of the steel reinforcement, freeze-thaw cycles, alkali aggregate reactivity. That includes the alkali silica reaction and alkali carbonate reaction. Chemical exposure has another effect on concrete, and that can be sulfate exposure, both externally and internally, seawater attack, and exposure to de-icing salts. Some other reactions are, abrasion, erosion, and physical salt attack. So today we are going to talk about the chemical reactions of the aggregate with the cement paste that can affect long-term durability. So in particular, that will be the aggregate, the alkali aggregate reactivity, and sulfate, which is actually going to be internal sulfate exposure. So what is alkali aggregate reactivity? Well, we have two kinds. There's ASR, when the chemical reaction of the hydroxy ions of the alkalis with certain silica components of the aggregate. This reaction, it forms a gel, and under some circumstances that gel can cause expansion and cracking. The other type we have is alkali carbonate reaction, and that is going to be between the certain dolomitic aggregate and alkali ions. We'll talk more about that in a minute. So, although ASR was first identified in literature in the late 1930s by Stanton, it was observed and documented in many dam structures even before then. It's been studied extensively for decades, and researchers all over the world have dedicated their careers to the topic with really no end in sight for finishing the work. It is a complicated chemical process with many variables and areas of study. We've seen cases in almost every state in the United States, and again, all over the world. It is a major cause of premature concrete deterioration. So how does it work? Just basically, you have a reactive silica component in your aggregate. Some of those reactive components are opal, tridymite, volcanic glass. So basically, it's a type of quartz that is not ordered. And you'll need also some sufficient alkali in the pore fluid and moisture. So once you have that alkali starts attacking the aggregate, you form an alkali silica gel. That gel expands with water, cracks the concrete, and once you have the cracking, it allows for more moisture to come in and start the process over and over. So it really is a cyclic reaction. Now, the source of alkali in the pore solution is going to come mostly from the cement, but we're studying more and more where that alkali could be from the aggregate. And also, you'll get a little bit of alkali-bearing water intrusion in certain circumstances. So here's just an example of some of the damage that you find from ASR. So we have a barrier wall, a lock and dam. So that is the physical damage that you can see. And then there are a few examples of the microscopical damage that we see to confirm the presence of ASR. So alkali carbonate reaction is not very common. It was first observed in Canada in the late 50s, and it's really mostly found in, it's just certain dolomitic limestones. Many of these ASR susceptible aggregate are actually not suitable for concrete due to their porosity, which makes them a little bit susceptible to freeze-thaw damage. So a lot of them really get flushed out in the C33 testing. Damage shows up pretty quickly here, but there is stark debate in the research community whether the damage to structures by ASR is actually being caused by alkali silica reaction, which is sometimes seen in correlation with damaged structures. So what happens with ACR is you begin to get dedolotomization of the dolomitic aggregate, and that causes expansive brucite formation. And we're finding a lot that sometimes that expansion is correlated with some ASR expansion from very fine microcrystalline silica within the aggregate as well. So that is still under debate. So test methods and guidance for alkali aggregate reactivity have had more varieties than geologists have descriptive terms for rocks. It's really hard to decide what to do and how to do it. There are a few guidance documents that have really mapped out a path to understanding the reactivity potential of your aggregate and how to use it in concrete without issue. These are, in the United States, we have the AASHTO R80, the ASTM C1778, and there are international standards as well. RILAM has a guide, and the Concrete Standard Association. The important thing to note about these guidance documents is they really are all in general agreement regarding the recommended test methods. And the United States guidance documents were developed predominantly from data and recommendations that were provided from the Federal Highway Administration ASR Development and Deployment Program. That really initiated in 2017 and went till 2013. So there were four primary scientists that led most of those investigations. Michael Thomas of University of New Brunswick, Benoit Fournier of University of Laval, and Kevin Folliard, University of Texas. If you go to the Federal Highway Administration website, you'll see a lot of the reports, well, all of them, the reports from these studies on there. It's really a result of decades of research from scientists all over the world. The test methods that are recommended in these guidance documents are based on rigorous method validation and correlation with field exposure sites and field history. They have put exposure sites all over the world in many different environments and different mixes, correlating the test methods to establish long-term performance, and also evaluating the long-term performance of current mitigation strategies. So the information they're getting from those projects really gives us the data we need to adjust recommendations and testing based on knowledge and data. Now, these test methods are not perfect by any means. They are evolving, and they will continue to improve over time. And if you look here, we do have an example of the Hawaii DOT and the Massachusetts outdoor exposure sites. So from the ASTM C1778, I'm going to use that because it has a nice flow chart that has been updated recently, and this really guides you, from the standpoint of aggregate production of how to evaluate your aggregate. So the number one thing really is a field history. Unfortunately, agencies aren't going to take your word for your field history review. So if you're not doing so already, you really would want to create a nice documentation history that you can use later and currently really to correlate your aggregate history with testing and performances. Petrographic exam is essential to know what type of rock you're producing and to uncover potentially deleterious components. Unfortunately, a petrographic exam alone isn't going to give you all the information you need to know about the potential for reactivity. If you look on this flow chart, there are dash marks and solid marks. If you follow the dash marks, you are going to assume some kind of risk for your aggregate. If you follow the solid approach, you are reducing your risk of your aggregate being reactive and you not being aware of that. So the two most common test methods that we have, and I'm really going to stick with the alkali silica portion of this right now because again, it is the most common. But there is an accelerated mortar bar method. It takes about 14 to 16 days. And the unfortunate thing about that is that the test results are generally not very accurate. Your best bet is to use the concrete prism test, which unfortunately does take 1 year to complete. But what you can do, if you collect the data and do the investment up front to evaluate your aggregate, you can then use the accelerated test method to monitor your aggregate. Because if you have the data to say that your accelerated test method correlates well with the concrete prism test, then you will be able to use that quicker method to monitor what you have and see if there's any changes. So part of this guide, it goes on to really tell you how you can mitigate your aggregate for use in concrete. I'm not going to talk about that today, but that is really part of the program. So you want to know what to do, keep calm and follow ASTM 1778. And I say that over the AASHTO only because ASTM is just more rigorously evaluated and it does take longer to get things moved in there, but it's because you have representation from researchers and all areas of industry to make recommendations for testing. So the guidance documents really are driving the specifications. Investment in testing may be high initially from a characterization of what you're working with, but then a subsequent testing regime can be driven from that existing data that you gathered, from requirements from your purchasers. Some agencies do require your tests to be, within 3 years old. And if you have some significant aggregate changes, you may need to do additional testing as well. But you really just want to know your rock and prepare for the worst case scenario to keep you from costly legal issues. Now, this isn't an easy topic. Like I've said, extensive research has been going on for decades, and we still haven't developed the perfect test to predict performance. I do suggest that if you're having a hard time understanding this, use a consultant who's knowledgeable on the topic, and they can really help you navigate the guidance and protect your investment. Looking ahead on the ASR issue, there are some promising test methods that are being evaluated at this time. Things, when I say they want new test methods, you want accuracy, and people just want results fast. There's a miniature concrete prism test and concrete cylinder test that is very promising. Some other Methods under development and validation include just modifications to the concrete prism test through RILEM. Turner Fairbanks has an ASR susceptibility test they're calling TFAS, using chemistry of aggregates to predict reactivity. The Texas A&M has a composite activation parameter and an accelerated cylinder test, and there are some autoclaves, concrete prism and miniature mortar bar tests. So I'm going to switch topics now and move on to the topic of iron sulfides. So iron sulfides are common accessory minerals that come in many forms: pyrite, marcasite, pyrrhotite, chalcopyrite, pentlandite. The most common is pyrite. And pyrrhotite's not far behind it. And what we have found is that pyrrhotite is the most problematic in concrete. So this is due, here we go. So the reason why these minerals are problematic is due to oxidation. So iron sulfide oxidation is something that has been studied for decades. There's extensive literature in the acid mine drainage area. So as they were mining for coal, you're uncovering shales, predominantly with pyrite in it, and that pyrite again reacts with oxygen and creates sulfuric acid, and that sulfuric acid can obviously cause a lot of damage, and it also discolors. Discolors rock, discolors, in this case, you see a roadway that is discolored. So it really caused a lot of problems. More recently, there has been research and studies and surveys looking at sulfuric-bearing geologic formations. There's some in Virginia, Pennsylvania DOT did this because as they were doing construction for roadways and cutting into bedrock that previously had not been exposed, they were coming up with issues, and that's what the one picture below where you have the iron staining in a neighborhood came from just that such issue. Related to aggregate production, access to air, the first sign that you have a problem is that you'll have a rusted stockpiles. So again, access to air is number one. And what we found is that material above the water table may have had some weathering already done, where the reaction had taken place previously, so you don't have the severe staining. But once you get below the water table, the rock hasn't seen air before, and that rust and oxidation really takes off pretty quickly. So when you're talking about having these minerals in aggregate and concrete, the oxidation again creates sulfuric acid. That is going to react with the concrete, the paste in the concrete, and form some secondary minerals, etronite, gypsum. These are expansive. They also will decrease the pH. And you'll get cracking, and in the worst damaged examples, you get the thomsite formation, which creates very friable paste. And it became so friable that you can break the concrete with your hand. I said previously, pyrite does not oxidize nearly as readily as pyrrhotite. concrete or other cementitious matrix, such as stucco, further protects the material, the mineral from oxidizing. Most of the pyrite issues occur when a grain is at or just below the surface. So this is commonly seen just as staining. Sometimes it'll progress to pop-outs or cracks. We have a lot of sidewalk stainings. In this case, this is a stucco home that showed the iron oxide staining on it. But with the pyrite, we really haven't seen the kind of damage that we have seen whenever pyrrhotite is present. And to talk about, there's two recent examples of this problem. The first started showing up probably around 2009, I think, maybe 2006, in the Trois-Rivières region of Quebec, where the problems really started within just a few years of construction. These foundations began cracking. And in the United States, we have an area of Connecticut which has shown the same or similar kind of damage. These structures were constructed in the early 80s. It really came out of one quarry in that area. It was a schist. The damage it took about 10 to 30 years mostly to be able to show up. So just to give you an idea of some of the difficulties with this. So these minerals are present in very small amounts. There has been evidence of some of this damage showing up in the Quebec aggregate when you only have 0.2 or 0.3% of by volume of pyrrhotite in the aggregate. So if you look at these images, the one on the left is a 4-inch diameter core slice, and those little bright particles inside the aggregate, those are the pyrrhotite. A lot of times we'll see that it is present with a lot of mineral phases. So pyrite, pyrrhotite, chalcopyrite, they often are found together. There's a number of factors that actually are not fully understood of why this pyrrhotite can cause damage in one area and not so much damage in another. Some of the factors have to do with the quality of the concrete. If you have concrete with high porosity, which enables more air to get to it, you're going to have more damage. We're looking at the crystal structure of the pyrrhotite. The pyrrhotite comes in a number of forms, and some forms appear to be more reactive than others. Your environmental condition is going to matter. We are finding that the relative humidity it does have a big effect. Buried structures that don't get as much access to air, much like those rocks beneath the water table, who doesn't get as much exposure to air. They seem to be more durable and not showing reaction. Unlike if you think about a foundation wall where you have that interior surface exposed to the air in your home, the damage really progresses quickly through those walls. So just last month, the U.S. Geological Survey put out a fact sheet, which can be found at the URL that I have listed there, and it created this map which only shows where the geology indicates the potential for pyrrhotite formation. And this is based on geochemical and physical processes of the geology of the region. This map, just to tell you, there's no verification or testing of aggregate in these areas to document that there is pyrrhotite present. It is just to show you where there might be. So right now, there's no established standards with limits for rejection of aggregate in the United States. The Connecticut DOT does prohibit the use of aggregates with greater than 3% pyrrhotite by mass by visual inspections. I don't think they've found any, since they started that in 2017. The Canadian Standard Association has been doing a lot of research, and they have developed a testing regime for evaluation of the total amount of sulfur in your aggregate and whether it has a potential for damage. That is part of it's actually an appendix to their standard, which means it is not mandatory at the time because they are doing additional testing to come up with the correct values. But they do have a nice program that I am going to go over real quickly, because really it is the best avenue for us to go down at this time. So part of it is a performance evaluation for the determination of deleterious oxidation potential of sulfide-bearing aggregates. The first part, you're going to do a field evaluation of the aggregate source with the geological survey and sampling, some field performance in concrete. If you have, concrete that's more than 15 years old that was using the same aggregate in an oxidating environment, you can test that to evaluate if a reaction is occurring or not. And then the last part is a laboratory investigation and interpretation. So the laboratory investigation, you're first going to look at the total amount of sulfur in your aggregate. And from there, you can identify how much of that total sulfur is sulfide sulfur. So right now, based on some European standards and information we have, if your aggregate has more than 1% by weight of sulfur, it's going to be rejected. Because even if it's just pyrite, it could cause, staining problems and such. If your total sulfur is less than 0.15, you can accept it. If it's in between, you'll want to test it further. And first, you're going to test for the sulfide sulfur. And then you're going to move on and test the potential oxidation issue. So the first thing is oxidation consumption test. I think that the limits they're using right now, if it's greater than 5%, you're going to go to step 3. And if it's less than 5%, you're okay. And the final step is mortar bar expansion, which has 2 parts to it. The first part is going to promote oxidation in order to determine expansion caused by the expansion products of the oxidation reaction. That actually, if you're above the level there, which is 0.1% after the 90 days, it could be ASR or iron sulfide. So you have to take a look at your mortar bar after that step. If you're at less than 0.10 after 90 days, then you're going to move to the second part, which is going to promote the secondary deleterious expansive minerals that form in the cement paste and cause the kind of damage you see in that image. So going forward here, research. There's a lot of research that is needed. They are doing it in Canada. They're doing it in the United States. I think the United States is far behind, but we're ramping up at this time. And we are working hard at ACI and ASTM to give some guidance on this topic. So,
all right.
We'll go on.
Thank you very much, April, for that very informative presentation. Hold with us for about 5 seconds as we switch and sanitize our microphones here. We will ask some questions. Before we start getting into all the questions here, just a reminder that as soon as this webinar is over, there will be a 3-question survey. So please be sure to take that for us, and that'll inform our webinars and presentations in the future. So here's a question in the questions tab. Have you used lightweight aggregates to help mitigate the expansive reaction due to ASR in concrete? It has been used successfully in the Western U.S. to meet C1260 testing. April, did you address that already?
No, I personally do not have experience with that, but I know that they're evaluating a lot of different materials to mitigate ASR. You have your supplementary cementitious materials that well-known fly ash, slag, silica fume, but what's getting more traction lately is the use of natural pozzolans.
Okay, thank you. Here's another question for pyrrhotite. Is RH of the concrete or the local humidity of the environment?
It would be RH of the concrete. And what we've been seeing is there seems to be a sweet spot. Some people may think that you really need a lot of water to get this reaction going, but it really is the oxygen that drives the reaction. And there seems to be a sweet spot. Don't quote me on this, but between like 50 and 70% relative humidity has been the highest damage.
Okay, thank you. Hold on 1 second. These questions are typed so small. Is colloidal silica something that is being for ASR mitigation in place of? I'm sorry, is colloidal silica something that is being for ASR mitigation in place of Class F fly ash? Does that make sense?
Yeah, so I mean, I'm going to assume that the colloidal silica, are you talking about the silica fume, or I'm not quite sure.
That's all I have for you. Yeah, sorry, that's all they typed. I apologize. Here's another one. Is it the 1260 test isn't accurate, or is it doesn't correlate to the field? If it's the test that isn't accurate, should we do more than 3 recommended samples per mix?
Well, it's actually both, and it's dependent on the aggregate. It is so widespread, but yeah, those rapid test methods just don't have a good history of accuracy. That is why it's very important to correlate that with the concrete prism test and your field performance. And when you have history of that and you have good correlation, then go with it. Especially because some of the agencies that are going to purchase your concrete, they are going to require, a lot of them are requiring like a 3-year test. So that's something you can get done faster than trying to do the 1-year test every 3 years.
Okay, thank you. What are some mitigation measures for the pyrrhotite? Is it cement reduction and SCM addition?
Well, there are no mitigations identified right now, but the more dense your concrete, the less air is going to reach the pyrrhotite, which is going to help protect you. So the better the concrete, the less potential for damage. And if you think about the cases that we have seen so far has predominantly been in residential foundations, and the quality of residential foundations is not as high as you would have with like a high performance concrete, or you know, something used for a dam or something like that.
Okay. Thank you. Is there any ASR test regarding fiber reinforced concrete?
I'm sure there is. Yes, because I think that that can help with the expansion if you do have some ASR.
Okay. What do you recommend for the shortage of fly ash to combat the reactive aggregate?
Well, that's why we're looking a lot into the natural pozzolans. Those sources are being evaluated all over the country. There's some areas that have more access to it than others. Yeah, I think I think that's the best we. Well, no, let me also talk a little bit about this in response to that question. A lot of the specifications that are coming out of the industry, like the DOTs, they are just telling you if you have, whatever concrete you're making, you just have to have 30% fly ash in it to mitigate any ASR. Well, that's a prescriptive approach. There are the opportunity for performance testing. So you can see how much do you actually need to mitigate your aggregate. And maybe you won't need as much as what is being specified by the DOT. And as long as you can show that, you should be able to use the concrete, or the aggregate, I'm sorry, for concrete.
Okay, very good. We're going to do two more here. How detrimental is using a crushed quartzite in concrete in regard to ASR?
Well, it depends on what concrete you're using it for, and how reactive it is. I've seen some quartzite that hasn't really been too reactive, and some that has. You're also looking at the availability of alkali. So, are you using a low alkali cement with that? You're not gonna have a problem.
Okay, thank you. I'm going to do one more good question here, but for everyone who submitted a question, we had lots of questions and we can't get to all of them. I'll make sure April follows up with an email to answer your question, if that's okay. Have you ever thought about using graphene for concrete mechanical reinforcement?
No, that's not an area that I would be.
Okay,
yeah.
we'll end on a different one.
More engineering.
Gotcha. Let's see. That one's already asked one like that. Hold on a second. Any comments on C1778 and natural pozzolans? It's right there.
Yeah.
Is that a little awkward? I can go with another one.
Yeah, I'm not really sure what you mean by comments. We're trying to incorporate the use of natural pozzolans into that standard. It's a little bit tricky on some of the recommendations, because natural pozzolans are really a different animal than the other SEMs. But it is definitely being worked on, and we should have some kind of resolution on that in the near future.
Okay. What are your thoughts about using pond ashes for ASR mitigation?
Yeah, there's been a lot of research on beneficial reuse of that material, and as long as it meets the standards for fly ash in concrete, and you're able to show that it's not deleterious, then I think it's a great opportunity to actually address one of the previous questions of what do we do with our dwindling supply of fly ash?
Okay. And again, thank you everyone for attending. April will respond to your questions. I'm going to send you this recorded webinar by Friday afternoon, and please take the survey that is about to pop up. Thank you everyone out there, and stay healthy.